This is Unit 5F. It deals with interference, polarization, and the nature of light. So what we have in front of us starts at the bottom as usual. We have waves arriving here and they are diffracted. Now they're diffracted in all directions, but we're only showing 4 of those directions. And we can see our wavelengths emanating here. Now if they arrive in the middle here together, or if we consider this middle point, we can see that the distance is going to be exactly the same. So from here and from here to here is going to be the same. So that means these waves are going to arrive in phase, and we get a constructive point here, so they reinforce each other. Now over here we have another constructive point. So why is it bright here? Well, it's because there's a distance here, there's also a distance here which we're representing to the left here, and if the geometry is just so, we can see that we have a path length of, let's say, 10, and if the other's path length is 9, so exactly one wavelength, one lambda difference, then they arrive in phase, or the phase difference is 0, and that's where we get our constructive interference. So whatever the amplitude was there, it will now be doubled and we get our bright spot. Now, just for reasons of saving space, we've looked at our destructive over on the right here, but many of the principles are the same, although the outcome is the opposite. So we've got a certain length here along this angle from this slit, and we have another length here. Now this time the path length here is 10, and here it's 1.5. Now it could be 20.5. It's the half that we're interested in, so the path difference is 1.5, which we can see there, but here we can more clearly see that the phase difference is a half. So these are exactly half a wavelength out of step phase difference here, so these will cancel out. So we've got a trough here combining with a peak, so we get the destructive interference we talked about earlier, and we get darkness there. Now the overall pattern, or the overall phenomena, we call an interference pattern. So light, what is light? This is a key question that people have worked on for many centuries, in fact, and the particle theory was put forward first by Newton and others. Then later we found interference phenomena, which we've just talked about, and then much later we again found evidence that it was more particle-like. So that left us with the question, light, is it a particle or is it a wave? Well, the answer is it's neither, in the same way that an apple is neither a football nor a grass. So you could make an argument that it's spherical, or you can make an argument it's green. It clearly has aspects of both, and this is a typical image to try and illustrate that, and I've got them here. So what can you say about light? Well, all you can really say, it's tiny packets of energy, and sometimes it's wave-like and sometimes it's particle-like, but actually it is neither. So finally then we have polarization. So if we look up here to begin with, this is a representation of light. I know we've just said it's particle-like, but this is one representation. So we've got an electric field and a magnetic field. If we look at that head-on, we can see that as a line, but nature doesn't really, it isn't neat, so something reflecting light will do so in all orientations, every single orientation you can possibly imagine. So polarization is turning that multi-orientation into just one, and there's 2 key ways that can happen. The first one is reflection. So here we're only showing 2 orientations just for simplicity. So the light comes in here, hits this surface, this water surface, half will go through, half the energy will go through, and half will be reflected. Now if that goes straight into your eye and you're trying to see what's below the surface, you have a problem, because this reflection is much stronger than what's coming from below the surface, and we get an image a bit like this. We really can't see what's going on. However, if we have a polarizing filter here in front of this eye, we can see that the surface glare is being cut out, and the light from below the surface will reach us. It's not shown here. So what's happening? Well, it's basically like a sort of prison bars, we've got our multi-orientation hitting here, and it only lets one orientation through, or more technically, one component. So half the energy goes through. So that this first filter does a very similar job to the water. Then our second filter, you'll notice it's at 90 degrees difference, so opposite orientation, and that will absorb all of it. And the result of that is we get an image like that, very easy to see what's going on underneath the water.